So I came in early today to edit the schedule, and I couldn't. I don't know why. But I've been talking about the schedule here. A couple of things, right? So schedule for the first 3 weeks. We're on Tuesday, right? For week 2, we're going to take our first quiz today. And our test will be Thursday of next week, our first test. Right, this is our grading scheme. And there's the idea for quizzes. So quiz 1, today it's a U sub and an integration by parts. Quiz 2 will be a trig power and then a trig sub. Quiz 3, Simpson's rule, right, where like I did the other day, I did an integral, got the answer, then estimate it with the Simpson's rule. Quiz 4, area between curves. And quiz 5, disk and shell. So the chapter 6 material will happen next week, so plenty of time for you all to ask me questions, right? And there's our homework, right? Homework 1 you gave me yesterday. Homework 2 Monday, right? Yeah. So they're both Mid, Trap, and Simpsons. The number 3 is 4 rectangles, and number 23 is, I think, 10. Right? Oh, it has left, right, and really?
Yeah, left, right.
And no Simpsons? Let me look at that one again then. Oh yeah, let's not do that one. I don't want to give you errors either. What did I give you? Oh, nice. Thanks, Dave. Thank you. Let's do 3 and 9 then. Say it again.
3 was the problem.
3 is not too bad. You're doing trapezoid rule, midpoint rule, with 4 rectangles. The thing that I see most students get wrong in number 3 is it's cos of x squared. So you're squaring the argument before you're taking the cosine of it. So just be careful, just be conscious of that. I'll have a lot of students actually do this instead. And right, it's just sometimes we get a little lazy reading, I think. That's good. So 2, 4, only 6 problems this time, right? But that's okay. Yeah. And those are the ones you're turning in, right? So you're still doing more, right? You're doing more, and those will get the special attention to turn in. I don't mind if you use some technology to do the 5-9. So I certainly don't mind that at all. Nice. What do you got for me? Any homework questions you want me to do? Anything you want me to do? Nice. So we got a nice little area between curves here. So this is a recap of yesterday. Um, I want to find the area between these two curves from 1 to 4, right? And it's pretty obvious that I have an upper minus lower, right? And this rectangle idea is going to come into play a lot today when we do our disk method, washer method, shell method, okay? Um, so it's important that I'm able to see kind of what's going on here. I want the area from 1 to 4 of the arctan of 4x minus the ln of x dx, right? So we want to, right? I would say to you, find the area between these two curves. You don't know which one is above or which one is below. You're going to graph it, right? Um, so you got something like that. It doesn't matter, but I do know my area is here, right? And I want to make sure I'm seeing that rectangle. I want to see that one rectangle of what I'm doing here, right? So most of the time, these are going to turn into two integrals, which is nice because now I'm asking you a problem in 6.1, and I'm getting two problems done from chapter 5, right? So it allows me to do a shorter test. I'm thinking 12 problems for the first exam. So it turns out to be about 10 minutes a problem, okay? So we're going to get this area, right? So we need two integrals. Arctan of 4x dx minus from 1 to 4 of ln of x dx. Good. So let's do those. Those are both by parts. Both by parts. So good practice for today. I'll call the first one star and the second one hashtag, and I'll just work on those two, right? So for my Leate list, what's my choice for U here? Yeah, the inverse trig, right? So arctan 4x, and then du is going to be 4 over 1 plus 16x squared, right? I need the derivative of the inside and the square of the inside. dv is just dx, so v is x. And now I have everything I need, right, for my integration by parts. Remember, I need uv minus the integral of v du, right? So it looks like x arctan of 4x. Right? You're not just copying, you're erasing me, right? minus integral of v du. Oh, that's a dx there, sorry. Everybody okay here? Anybody hear me? Yep. Kind of weird in that I'm going to evaluate this from 1 to 4. I'm going to get some kind of decimal out of it, right? It's not pretty. But I want you giving me some exact answer and then, right, get me a decimal from that. No, sorry, it was arctan of 4. Okay, the other integral, ln of x. Again, by parts. I'm cheating. I'm using I just did this problem, so. And then the decimal equivalent, right? Everyone able to do those integrals? Anybody able to do those integrals? And then I want to test it, of course. So int, I start typing integral, right? From 1 to 4. And I had arctan of 4x minus the ln of x. I should, and this is just a technicality, but I should wrap all of that. Anytime it's multi-term, right, I want to make sure I'm wrapping all of it because it's got to be associated with the operator dx, right? The integral and the dx are telling me to get the area. So you can see what I'm going to do on a problem like this is I'm going to put in those other integration methods into this problem, right? So maybe there's a by parts, maybe there's a trig substitute, et cetera, et cetera. So you just got to be ready. I will give you my old tests. I still have to do that, but I'll do that this week for sure. Cool. Well, we got a pretty busy day with new material, so we might as well just get started on it. So we're talking about 6.2 is the disc or washer method. So the idea about the disc method, and it's a disc if it's a solid circle. It's a washer if it's, have you seen a washer before? Have you put together a piece of IKEA furniture before? The washers protect the wood from when the bolt goes on, right? So so it's a disc if it's a solid circle, and it's a washer, right, if it's got that hole in the middle. But both have basically the same formula, right? So if we're thinking about the disc method, if I'm looking sideways, right, you can see I'm going to rotate this and get a bunch of coins stacked. Okay? So think about that coin. The area is pi r squared, right? So I need a pi r squared. Delta x is the thickness of each coin, and that gives me volume. Right? You with me there? Pi is a constant. R is a variable, so r squared is in second dimension. And then I need the thickness of the coin. That's my third dimension. That gives me the volume. Yes? And what's true about the other coins for the washer is, well, there's just a hole in the middle. So in that one, my volume is going to come from pi of big R squared minus little r squared, right? So the biggest radius minus the smaller radius. So kind of you'll decide at the end whether you have a disc or a washer, and then you'll figure out your radii. And the way you do that is you draw a picture, and then you take a cross section. Okay. So we talked about the method a little bit last class. I'll try and write it down as well today, kind of in a step by step. But just talking about it at first, here we go. Let's do a problem. Yeah, big R squared is the outer, so that's capital R, and this one is little r.
My intuition would be just big R minus little r squared.
So because I'm doing the big outside circle, there's a pi capital R squared, and then I'm cutting off that little one, there's a pi little r squared.
Okay, yeah.
Yep. So they're really the same formula, right? The little r, the other radius here is 0, right?
Yeah.
Yeah. So let's just do a problem. Let's take let's take square root of x, and x is 1, right? Let's take that particular area. Sorry, y is 1, right? So we're doing this area here. And I want to rotate that around the x-axis. So the problem is find the volume bound by y equals square root of x, y equals 1, and x equals 0. Right, so you're seeing all of my sides here. X equals 0, y equals 1, right? So that region, and I want to rotate it about the x-axis. So I like to redraw, once I have my area, I like to redraw with my ghost. I'll put the ghost in. And you should be able to see that it's, if I turn it sideways, right? If I turn it sideways, I want to be thinking of a glass, but the inside is hollowed out into a bowl, right? Yeah. So if I take a cross section of it and look at the base of that cup, which is on the side on my wall, right? The base of the cup is round, right? Yeah. So if I take a cross section of it, okay, and remember my cross section will be that one rectangle rotated all the way around, right? That one rectangle rotated all around. If I can see the cross section, I definitely see the disc. Sorry, the washer, right?
Yeah.
So it's that original rectangle that I have to deal with. Remember, if I'm doing the disc method, which is disc or washer, it's perpendicular to the axis of revolution. So since I already had my axis of revolution, I know my rectangle's got to be perpendicular to the x-axis. I want to go from the axis, right? From the axis of revolution to the top of the rectangle to get my big radius, right? So this distance right here is capital R, and then this distance here is little r. You see that, Noah? Yeah. And what you need to remember is I'm always doing an upper minus lower or a right minus left. I want my radius to be positive. Okay, so I have to do the higher minus the lower. And it's the top of the rectangle to the axis of revolution is my upper radius. The bottom of the rectangle to my axis of revolution is the lower radius. Every time. And they get pretty friggin' tricky when I start moving the axis of revolution. Meaning I don't make it the x-axis. I make it x equals or y equals minus 1. But the process is the same. Okay? So we're finding our region. We're ghosting it to kind of create the 3D volume. We're looking at a cross section to decide which formula we're using, right? And then we're just figuring out the radius. So first of all, I'm going to be doing, I know it's a pi r squared problem, right? But and I'm doing it with respect to x, right? And I can tell that by the rectangle. The width of the rectangle is a delta x, turns into a dx. So my x's go from 0 to 1. And what's my upper radius? 1. And the lower radius is square root of x. And you see most of these, they turn out to be very, very simple, right? So that particular volume is pi over 2. So now, of course, we can check that we got the integral right, right? We certainly can check that we have the integral right by typing in that particular piece. So I had pi times the integral of 0 to 1 of what? 1 minus x, right? So half a pi. Now, of course, the issue is if you don't have the integral right, right? So you got to try and put down as much on the paper as you can to justify your work, so that I could give you some partial credit if you get it wrong, right? So it's really helpful to see all of these pictures, the original region with the rectangle, with my 2 radii, the cross section, the rotation, right? And etc. We'll play around with some GeoGebra today. Let's do another one of these. So let's create a football. Let's take our sine from 0 to pi and rotate it around the x-axis. So from 0 to pi, there's my sine, correct? And I want this particular area. I want to draw that rectangle in there. And this one is pretty obvious that it's going to be just a bunch of coins stacked, right? Look at the rotation of this. I like to draw the ghost and then kind of, right? So we got a, I don't know, pistachio, maybe, right? Rugby ball, I don't know. Yeah, grape. So my cross section is just a solid, right? So what's the question? Find the volume. Of y equals sine x and y equals 0, right? From x equals 0 to x equals pi, right? I've got to give you all the kind of endpoints of what I'm talking about, yes? About the x-axis. Yes, we're getting the idea. When you take, for those of you doing physics, chemical engineering, when you take multivariable calculus, you'll be drawing a lot of 3D pictures. You'll probably be using a program, MATLAB, I think. But it's a good idea to practice sketching things in 3D as well. So what do we need? Well, it's a disk, right? So I just need my upper radius, which is sine, but I need it squared, right? Right, pi r squared. So this is a power reduction, which is 1/2, I forget it. This is why you have a formula sheet, because I can't even remember. Yeah, so 1/2 minus cos of 2x over 2. So there's the power reduction for sine squared. Will you double check me there on my integral of cosine? Sine of 2 pi is 0 as well, right? And units cubed, who cares? You'll actually see that integrals can give us just a number. It can give us the area. It can give us a volume. It can give us a force. Right? So units will kind of take care of themselves if you think about it. This is a nice one to check because I'm going to go all the way back to my sine squared, right? I'm going to go all the way back to my sine squared when I do my integral here. So pi times the integral, int, of 0 to pi of sine squared x dx. And what did I get? Pi squared over 2? Right, so nice way to double check. The key here is to not panic if you get something, if you check and you realize you got something wrong, right? That's important, that you're not going to put yourself into a panic if you can check yourself and you might not have it correct. And what would be the mistake? I guess what I mean, where's the first place for my mistake is that power reduction, right? So double check your power reduction, make sure you have all your trig identities on your formula sheet, all your derivatives, any kind of step-by-step that you might have. That's an interesting problem if I ask you to rotate around the y-axis. So that's what we're going to do now. So let's find a volume of the region bound by y equals sine of x, y equals 0, x equals 0, x equals pi over 2. About the y-axis. So we're taking x equals 0, x equals pi over 2, right? Y equals 0 and y equals sine of x. So I can see my region is here, but I want to rotate it about the y-axis. So again, kind of that glass, but maybe the drain funnel, right? Like when you empty a sink, you can see that funnel hollow in the middle. Since I'm on the y-axis and I'm disk method, right? I'm disk method. How do I know I'm disk method? Well, right now that's what section we're in, right? But I need a right minus left for my rectangle, right? My rectangle's always got to be perpendicular to the axis of revolution if I'm using the disk method. Disk or washer. And in this particular case, you should see I have a big radius and a little radius, right? So from the axis of revolution to the end of the rectangle, from the axis of revolution to the, you know what I mean, beginning and end of a rectangle, far right, far left, that type of thing. But I have to keep things positive, so I want to make sure that I write that R is 1 minus 0. Capital R is 1 minus 0. And I've got a problem here, right? Because I'm doing this in terms of y. I have to solve my equations for x. So how do I solve this for x? Very good, class. Now, this actually turns out to be quite nasty once I square these. I don't even know if I can do it. I don't even know if I can do this problem, but I just wanted to take a look at the setup anyway.
Even though it's not a washer.
Yeah, well, this one is a washer, right? If I cut on that cross section, yep,
Yeah.
yep,
They-
yep.
yeah, okay. But the area above-
Yeah. So this one, I don't even think we can do this one, but it's just the setup is good, and of course we can do it on the computer, but we get a volume of pi times. My heights are going from 0 to 1, right? Because remember I'm in terms of y now. and I have 1 minus arc sine squared x. Sorry. Arc sine squared y dy, right? I don't think I want us to try and solve this, because what I would do if I got this problem and I didn't know what to do with it, and I don't, I'm going to turn it into a shell method, because shell method is parallel. So parallel to the y-axis would give me a height of sine again, which is kind of what I want. Yeah, pretty nasty. So you can see what's going to happen to our problems is, again, these washers or disks or these methods will all have to do integration by parts. So I'll have to do a power reduction or something like that. So good, let's take a look at one from the book. And where it gets tough is where I start changing my axis of revolution, and that's what I'm going to do now. I guess 11 is fine. Y equals 1 plus secant of x, and y equals 3 about y equals 1. So 6.2, number 11. What the book tends to do is give you all of the setup is tough, okay? But the integral is easy. And what I tend to do is make the integral difficult. So you have to do a method from chapter 5 when you're finding this volume. So let's look at it again here. What do I have? Y equals 1 plus secant of x. Y equals 3 about y equal 1. I probably need some help on this. But I certainly can draw the cosine curve. Which will help me draw the secant. Plus 1, and then y equals 3. So I'm cheating that a little bit, right? You understand? I drew the cosine curve to get my secant curve, and then I added 1 to it to move it up, right? And then I've got that line y equals 3, so it's cutting off a piece of my secant, right? And so I'm going to do it on Desmos just so you see it, okay? So y equals 1 plus secant of x. And y equals 3. So I think I actually want that whole, right, that whole region here. Now that I draw it again, I think I want this whole thing, because it's not telling me x is 0. Now that is symmetrical, so I can cheat it, right, and just do half and then double my solution. But look at where I'm rotating around here, right? I'm rotating around y equals 1. So I'm going to draw the ghost. Right? And remember, so really kind of strange. And the outside of it is a perfect circle, right?
Like a yo-yo.
Yeah, like a yo. It does look like a yo-yo, right? Or the a car rim, right? So here's my axis of revolution, y equals 1, right? And I need to be perpendicular, which is nice. So there's my rectangle. I clearly see a cross section of a washer, right? Do you agree? All of this in here is empty, right? Only that outside piece is solid. Yeah. And I need, so my upper radius, my bigger radius is right to the height of that rectangle to the axis of revolution. And I have to do upper minus lower. So capital R is what? 3 minus 1. Right? That upper piece is the height of 3. And the axis of revolution is at 1. So upper minus lower, 3 minus 1. The little radius, right, is the curve, right? Right? The little radius is here. Yes, you with me? So I need the curve minus 1. So 1 plus secant of x minus 1. So capital R squared is 4. Little r squared is secant squared. You can see what I mean by their integrals are too easy. So I get the volume equals pi times, oh, where am I meeting? Pi over 2, right? You agree with that? That I'm meeting at pi over 2? Let me graph x equals pi over 2 here. No, I'm not meeting at pi over 2. Shoot. No, it's pi over 6. Sorry. But let me write it anyway. So I know my intersection is right here, right? That's where the two graphs meet. So I know that what 1 plus secant of x has to equal 3, right? Or secant of x has to equal 2, which means cos of x equals 1/2. So pi over 3. Let me double check that. Yep. Yeah. And I actually, so I made a mistake here because it's minus pi over 3 to pi over 3, right? So setup is tough. Every time, setup is tough. Their integrals are easy. What's this integral? Do we have it instantly? Well, 4x for sure, right? And what's the antiderivative of secant squared? See, too easy. Right, derivative tangent of secant squared. I know I could just double my volume, so that's what I'll do. I'm going to double the volume and go from 0 to pi over 3, just so I don't have to. Tangent of pi over 3. Somebody help me. Square root of 3? Yeah, square root of 3. Agreed? Tangent of pi over 3 is square root of 3? No? Yes? Thank you.
1/2.
Thank you, yes. So I want to double check myself here. So what's the difficult thing here? What are you thinking? I mean, this is the first time you're doing these, most likely. Say it again? Yeah. Yep, yep. And I didn't quite do what I said I would do. I like to see the region, then to draw the ghost, you know? So draw that ghost 1, 1, right? And then you've got the and then the cross section, and then the cross section. So then you know you're dealing with, right, the one radius or the two radii. Coming up with the intersection was not that obvious, but it was easy once we realized it, right? Integrating was easy. Let's double check our integration. So Desmos, I got pi times the integral of negative square root of 3 I'm sorry, minus pi over 3, right? And then my function was 4 minus, forget, 4 minus, oh no, 4 minus secant squared, right? Yeah. So about 15.4, and then I'm going to take my result and see if it's correct, right? So 2 pi times 4, no, I like this last one, 2 pi over 3 Then I had 4 pi minus 3 rad 3. Uh-oh. Oh, I got a mistake here in my... No, I see it. Yeah. Nice. That's why I like math. I like to be right every now and then without having to argue with somebody. Yeah, no opinion. No opinion needed. Cool. Let's do another one. So as I start moving things get a little bit trickier. Let's do 17. So I have y equals x cubed, right? Square root of x. I can see the region bound, but I'm rotating it at about x equals 1. So 6.2, number 17. Y equals x cubed. Y equals square root of x about x equals 1. Okay, nice easy picture to draw, right? Even if I didn't have a computer. But you can see my region here. This is y equals x cubed. This is y equals square root of x. And here is my axis of revolution. Yeah, yeah, that little, that little piece right here. So this is my region. And my axis of revolution is a vertical, so my rectangle has to be a horizontal. This is the trickiest thing about this. And then when we do our shell method, we have a different process. Okay. So I draw the region. I look at the axis of revolution. That helps me draw the rectangle, right? So this is a right minus left rectangle. So I already know I'm doing my volume in terms of dy, right? Because that piece of the rectangle is a delta y, right? Or it's nice to, you can see it as a part of the y-axis, right? You can see that rectangle piece there as my delta y. So my radius, look at the longer radius. It's this piece, right? There's my capital R. But I need the radius to be positive, right? So I need right minus left. And so capital R is what? 1 minus the black curve, which is square root of x. Right? I'm gonna try and ghost it here, okay? Just give me a second here. So I'm gonna ghost it like that, right? And you can see the outside is like a cereal bowl, right? But the inside is like that drain again, that cyclone. I'm upside down, of course. This is not easy for some students, I know that. To be able to visualize something. It's like playing chess without the pieces. It's not easy, right? But as you practice, you'll get a little bit better at it, and you'll see when we do these things on GeoGebra, we'll get a real nice picture of it, okay, that you can rotate around. So my little radius is what? It's 1 minus the other curve, right? X cubed. Okay, but here's the problem. I'm in dy, right? I'm in terms of dy. So I have to have these things solved for in terms of y. Sorry, in terms of x. So if y equals square root of x, what do I get? X equals y squared, right? And if y equals x cubed, x equals the cube root of y. Oops, sorry. Oh yeah, that's right. Yep. So my radii actually are different, right? The capital one is 1 minus y squared, right? And the little radius is 1 minus cube root of y. And then I have to square them. Yuck. Yuck. But not difficult, right? Now my y's are going from 0 to 1. My x's are going from 0 to 1 here as well, right? But when I'm doing my integral with respect to y, I've got to get the bounds in this direction. Yuck. But it's just polynomials. It's not like it's difficult to do this integral. Just horrible. So I guess I would probably be working on this on the side. But you don't need me to finish that integral, do you? No, right? It's just power rules, right? I mean, the setup is far more difficult than doing this integral, right? Nice. Let's take a look at GeoGebra. And I'm just going right up for disk method. Let me see if I can. I think I was doing this Joseph Manthe yesterday. I couldn't remember if I could change my function or not. Oh yeah, yep, yep. Nice. Now here, the real issue is, it's going to be hard for me to. Oh no, maybe not. Let me see if I can get a nice picture of that one function here. Yeah, this one seems to be fine. My function is 4 minus secant squared, right? Let's see what happens if we do that one. And I went from what, minus pi over 3 to pi over 3, right? Oh boy. Oop. There we go. Oh, negative though. Pretty nasty. It won't give me a good picture.
It's solid. It's just,
Yeah. Yeah, it's funny. It's the tire, right? It's exactly the tire. Um, but this particular one doesn't. I don't get to see the nice interior for some reason.
higher up.
Yeah, you're using the same one? No.
No, I like this. I like the front portion of it. Right? Yeah, me too. I don't know if you like zoom out or
Hmm. And you rotating?
something. Yeah.
Oh, I know why. Because I'm putting in the integral. I'm not matching my picture because I'm putting in the integral once I've figured out r and r little r, and then I squared them, etc. So it's not going to give me the same picture as this original one. Hmm. But that's okay. So I don't know how to get that picture. So I have to think about that. How could I even get that original picture? I don't know if I can. What's that? Yeah. What's that? It's just the rotation. Yeah. 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 But remember, it's not the original picture. This is.
Yeah, I know.
Yeah.
I'm
Yeah.
putting the same stuff you are getting in your picture.
Can I see?
Yeah, is this what you're getting?
Yeah, exactly.
Yeah,
Let me see.
this.
What?
Same interval, same push.
That's weird. And you did 8. And is 8 for you, Noah?
Is it a B?
I mean,
Number of
if they're
discs?
solid, it doesn't matter.
Oh, number of this. Mine's at 9.
Okay.
Yeah.
If it's solid.
Yeah, that's weird. I don't know. All right, let's take a break and then we'll do shell method, okay?